So now that we've gone over translations and truth trees, we're going to be spending the rest of the semester looking at natural deduction, which is probably the one thing that most logic courses spend most of their time on. In this presentation, I just want to go over the basics of natural deduction, explain what it is that we're doing, what the different lines are, and just sort of what you're going to see in the structure of a natural deduction problem. And then I want to go over the first three rules, which are arrow out, ampersand out, and then ampersand in. First, let's just go over the basics of a natural deduction problem. And so, if you remember from truth trees, we get these things called sequences. I'm just going to write one up here. This will be the first one that we prove in the course, which we'll see on really the next slide. But I just want to use this sequence to show you what a natural deduction setup looks like. So, what we have here in our sequence, as we talked about before, are premises. So these two things are premises. And this is our conclusion. We'll always only have one conclusion. So a natural deduction problem is really just a step-by-step process as to saying, how do we get from these premises here to this conclusion? And we're going to have 10 different rules that we can use to get from premises to our conclusion. And as we go through, we'll build up the rules, we'll build up different ways in which we can prove more elaborate sequences than the one that you see here on this slide. But the idea is to start from the premises and reach the conclusion using our 10 rules. So the structure of a natural deduction problem begins with the premises. We list the premises in lines 1 and 2. And we'll have however many line numbers we'll need down below. This is telling us just what line number we're operating on. So this is just keeping track of which step are we on. So this is just step number. What we'll see over here are premises. So these are numbers that are associated with specific premises. So what we'll have is this premise is on line 1, so it gets signified as 1. This premise is on line 2, so it gets signified with line 2. What we'll see as we do proofs on the later slides is that your premises numbers will show up in this column all the way down. You can have combinations of them, you can have one of them by themselves, but the idea here is that this is your sort of justification or your sort of source for where you're getting these sorts of moves from. Well, with that, we have over here our justification. So this line, or this vertical column here, is going to be your justification. In your justification column, you're going to have your premises set up at the very beginning, and your premises get marked actually with A's, not P's. That's my bad, because they're assumptions. I'll just fix that real quick, make it look a little bit better. So these are really get marked as assumptions. But as we go through here, on further lines down, you'll have line numbers plus rules. So you'll have where you're getting the information that you're using as referenced by line numbers. So for instance, we could do 1 and 2, and what we'll see is arrow out is going to be our first proof on, like I said, the next slide here. But what you'll see are, again, line numbers and the rule that you are using on those line numbers. A lot of natural deduction is like a matching game. What you'll be doing is you'll find pieces within the proof somewhere through these lines, and you'll say, well, with this information, I can use this rule, and using this rule on this information, I get this result. And then you put that result here on this line. And then you go back through and you look at all the different things that you have, and then you say, well, I can also derive this from what I have and my rules. And the ultimate stopping point is going to be your conclusion. The last line in every proof you'll ever do is going to be the conclusion that you see here. And again, this will require the line numbers that you're using and the rule that you're using, but you always know that your conclusion will be the very last thing to show up here. Your premises show up in the first lines, and then your conclusion shows up the very last line. It will be your job to figure out how do you get from these premises to this conclusion using the rules that we have at our disposal and the information in the actual proof itself. But on this slide, I just want to point out that there are 4 different things that you'll want to know. There are 4 different columns. You'll have your premises column here. You'll have your line numbers here, which are just going to be 1 through however many. It's just saying this is what line number you're on. This is going to be where you put the actual information that you get, what you derive from previous lines. They'll go here in the middle. And then at the very far right side, you have your justification area. So premises number, step number, your derivations, and then your justification. As we go through, it'll make more sense, but those are the 4 elements to a natural deduction problem. And then what we'll be doing is we'll be introducing rules as we go, and it will help you be able to maneuver from the premises to the conclusion. So we're going to start with the arrow out rule. It's the one that we usually start out with in logic. It may not be the easiest one, but it's the best one to begin with. And what I'm going to use here, instead of letters, and it will make sense as we move further along in the proofs, I'm going to use squares and circles. So say that I have a square, arrow, circle. And then I have square, and I'm looking to derive circle. So what I'm going to do, if you remember from the previous slide, is I'm going to start by listing my premises on my first 2 lines. I'll give this first premise the number 1 because it's associated with the line number 1. I'll give this premise line number 2 because it appears on line number 2. Now I want to mark both of these as an assumption. That's just what we do with our premise. Our justification for premises are they're assumptions that are given to us. So with these assumptions, with these premises, we can try to derive our conclusion. And we can derive our conclusion with this basic information. From square, arrow, circle, and square, so we've got square, arrow, circle here. We've got just square by itself here. We can derive circle by itself. And how we justify this is by 1 and 2, because those are the 2 pieces that we need. And what's the rule that we use? We're using arrow out. So when we do a proof like this one, it has two different pieces that you need. You need the arrow statement, the conditional statement itself here, and you need the antecedent or left side of the arrow here. And if you have those two pieces somewhere in your proof, you can go ahead and separate the circle from the arrow by doing arrow out and citing the two places where our pieces, I'm going to refer to these things as pieces, the things that are circled or squared or boxed in orange and green. Those are our pieces. And once we have those two pieces, we can derive our conclusion from them. And what we're going to do is we're going to cite the line numbers in which they come from. Here it's 1 and 2. So the last thing we need here is our justification or our premises. And how we do this is we're going to look at line 1 and we're going to look at line 2. Whatever numbers are next to line 1, we're going to put there. Whatever numbers are next to line 2, we're going to put here. And so as we get more complicated, that's the best way of understanding how we're going to make sure that we keep track of our premises that we've used in this in each of our proofs. The idea is that we can keep track of where the information we're using comes from. And so this is the most basic proof for arrow out. It's just showing the rule. Our rule is that if you have an arrow and you have the left side to that arrow, you can get the right side. Now, the reason why I'm doing squares and circles will be evident on this next slide where we go over just a couple examples. Now I want to go over two examples for arrow out using actual letters, not just the shapes that I was using before. But just to remember, our rule is if you have an arrow, a square arrow circle and the square, you can derive the circle. So let's do this one. As I said, we would do it as the first proof in the class. Q. So we'll do the same thing as we did in the previous slide. I usually just start with these line numbers just because it's easier. Then put our premises on each line, mark them as assumptions. Now this premise shows up on line 1, this premise shows up on line 2, so we're good there. Now we have, and this is why I did the squares and circles, because you have a square here, you have a circle here, you have the square here. That means you can derive, you can derive your circle here. And so what's in our circle up here? Well, it's just Q. So from lines 1 and 2, because those are our pieces, we have the square, arrow, circle in the line 1, and we have square by itself in line 2. So those are the two pieces of information we need. And then what's the rule we're using? Well, we're using the arrow out rule. So we cite the arrow out after we cite the two line numbers of which the information we needed to use that rule comes from. So we have it there. And then we cite lines 1 and 2. Why do we cite lines 1 and 2? Because we look at line 1. What's the number next to line 1? It's 1. What's the number next to line 2? It's 2. So we put both of them right there, and that is our proof. We just proved the P arrow Q, P therefore Q sequence. Now, it's important to realize that identifying the main operator is immensely important when we're doing natural deduction, because you can only use the rule that's associated with the main operator in one of the lines of the derivation within your proof, speaking here. So when you're looking at what you have here, you got to identify the main operator, because that is the only rule you'll be able to exercise on that part of the proof, or on that line specifically. So in this second example, let's do something you haven't seen yet. Actually, I'm going to erase that, give myself a little bit more room. T or S. All right. So now this looks really complicated, because we haven't even talked about what a double arrow is. We haven't talked about what a wedge is. In our proof structure, in our natural deduction, um, I know we've done truth trees on them, but we haven't done natural deduction on them. So you might be like, hey, how in the world am I going to do this problem? But it's the same exact thing that we have over here on the left hand side, and I'll show you. So we have P double arrow Q arrow T or S. And that's an assumption that we get from premise 1. We have P double arrow Q as an assumption here up in 2. Same thing as before. Both of these are premises. They get assigned the number that they appear at. So since the first one got written on line 1, it gets a 1 next to it. Since the other one got written on line 2, it gets a 2 next to it. So that is that. Now, let's use the square circle thing again. Here is the left side. The main operator is the arrow in between, because I've got parentheses demarcating the double arrow as P double arrow Q, and I've got parentheses demarcating the T or S as something separate too. So the main operator, again, it's important to be able to identify it, is our single arrow. So the only thing I can use on what appears in line 1 is the arrow rule. I can only use the arrow out rule. So I've got a square, and I've got a circle. Well, my square appears here in line 2. It's the same exact thing. It's P double arrow Q, P double arrow Q. So this is just like saying the same thing that we saw over here. I have the same exact setup. I have an arrow, and I have the left side of that arrow. So since I have an arrow and I have its left side, I can write its right side. And where am I getting the pieces from? I'm getting them from 1 and 2. Which rule am I using? Using arrow out. And just also for visual, this is my circle. And then we're going to look at what's the number next to 1. The number next to 1 is 1. The number next to 2 is 2. So there's that. So again, two sequences that look fundamentally different from each other. They get proved in the same exact way. Why? Because their structure, which is what we're interested here in natural deduction. Again, we're proving the validity of these sequences, and thus we're looking at the shape of the argument. And so both of these get proved in the same exact way because they have identical shapes. Now, if we were to carve up the sequence on the right hand side a little bit more, there would be more involved with this proof. But the proof itself is the same exact 1 as we see on the left-hand side. Just the information that's within it and what we're deriving is slightly different. But that's why I use the squares and circles a lot in this class to sort of show you the rules getting exercised, um, and how it sort of makes sense when things look a little bit more complicated than what they actually are. Let's do the same thing as we did before. Let's start with squares and circles and prove this. So the and out rule is super simple. What it says is that from an ampersand, derive either side. One ampersand out. So the most basic proof for ampersand out is that you will be given an ampersand here, as we were in our premises here, or in our as our premise here. And what that says is that from a left side and a right side, you can pick either or, and you'll just separate it off from it. So this could be square, this could be circle. It doesn't matter which one. It's going to be the same exact proof. And here, we only have one premise that needs, that's going to justify our derivation of one of the sides. So in the last one with arrow out, we needed two numbers. Most of the rules we'll see will involve at least two numbers, but there are a limited few that do only have the one number. It would be ampersand out and then also double arrow out are both just single number uh, justifications. So that's why we only have one number here, because the rule says all we need is an ampersand to be able to break it apart. And that's all we're really doing here. We're saying we're going to get rid of the ampersand. That's the out part of ampersand out. We're saying we're getting rid of this ampersand and we're going to take one of the sides. We're either going to take the left side or we're going to take the right side. The same rules going to get cited in both instances, and the same line number is going to get cited in both instances because that's where it's coming from. It's coming from the same information that we see in line 1, which is our premise. And then since the only number that's associated with line 1 is 1, that's what goes here in our premise line for our second line in the proof. So that's, again, the most simple sort of understanding of the ampersand rule. So let's move on to a couple of examples. So let me just rewrite our rule up here. From an ampersand, we can either derive its left side or its right side. So we'll just start with P and Q, therefore P. So we'll only have one premise, and since it appears on line 1, it gets marked as line 1. We're only going to have a second line here. And what we'll end up doing is, so we have this ampersand, we got this ampersand right here, and we can just go ahead and use our rule to separate it. So since I'm looking to derive P, I can just write P there. Where am I getting this from? Well, I'm getting it from line 1, because that's where my ampersand is at. And what rule am I doing? Well, I'm eliminating the ampersand, so it's going to be ampersand out. Then, well, look at the number. I got number 1. What premises are next to it? Well, it's just the number 1. So there's that. That is all we have to do for that proof. If we were to do P and Q, therefore Q, it's the same exact proof. Start with P and Q. Assumption 1. We'll derive Q instead of P here by doing 1 ampersand out. Same thing as before. So with the ampersand, you get to pick which side you want to take out. Either left side, right side, it doesn't matter. From that, we can do, again, the same thing we saw with the arrow out. So this looks very simple, but it's the same thing as before. Remember, square, arrow, circle. Here's my square. Square. Or, sorry, square, ampersand, circle, square, ampersand, circle, circle. So it's following this rule. Now, if I were to give you something like this, not, say, P, wedge, Q, and L, double arrow, M, therefore, not P or Q. What I have here is my assumption, line 1, my premise, also gets assigned line 1, but it's still a square and a circle because my main operator is the ampersand in between them, right there. And since the ampersand is the main operator, I can use my ampersand rule. So I will, and line 2. What am I trying to derive? Well, I'm trying to derive the conclusion, so I will just go ahead and write tilde P or V, or sorry, P or Q. Where am I getting that from? I'm getting it from line 1 because that's where my ampersand's at. Which rule am I using? Well, I'm using my ampersand out. And what number is to the left of that premise? Or sorry, what's the number next to the 1? Well, I just have a 1. And same thing could be said again. Say if I were to do same 1, not P or Q, and L double arrow M, and I'm looking to prove L double arrow M. We would start by listing our premise, Q, as an assumption, mark it as number 1 since it appears on the first line, and then since the main operator is the ampersand, I can just derive the right side, L double arrow M, from 1 ampersand out. Same thing as before up here, except for instead of doing square and circle, therefore square, I'm just doing square and circle and then deriving the circle. So again, same rule up here. So those are the most basic versions of the ampersand out rule. Let's do the ampersand in rule. So now that we've seen the ampersand out rule, let's do the ampersand in rule. And it's actually the reverse of the ampersand out rule. So our ampersand out rule was to say if I have an ampersand, I can derive either square or the circle from it. This is, and whenever you see me draw this line here, that's just saying that it is the derivation divider, we could say, which is I have this stuff up above it, and from that information I can derive what's below the line. So this was our ampersand out rule. Our ampersand in rule is going to be, like I said, the opposite, which is going to say if we have two things, we can just put an ampersand between them. So that will be our ampersand in rule. So again, using our squares and circles, say that if we were trying to prove this, we would start by listing our premises, which are square and circle, and we mark them as assumptions. We would give the square a 1 because that's the line that appears on. We'll mark the circle with a 2 because that's the line it appears on. And so from this information, you can put the two together. If you have two things that appear in your proof, you can just put an ampersand between them. And what you'll cite are the two places where that information comes from. Where am I getting my square from? Well, I'm getting my square from line 1. Where am I getting my circle from? I'm getting it from line 2. What's the rule I'm using? I'm using ampersand in. I'm putting two things together and sort of binding them together with an ampersand. So what we'll do is we'll look next to our number 1, we just have a 1. We'll look next to our number 2, we just have a 2. And then that would be the proof. The same thing applies, say if I were to do and square. So reversing the conjuncts. So when we talk about an ampersand, we're talking about a conjunction. And the different sides of an ampersand are called conjuncts. So with our ampersand rule, it doesn't matter how the conjuncts appear in the actual proof. So say if we were to do this, same thing as before, square, circle, assumption, assumption, square appears on line 1, so it gets a 1 next to it, circle appears on line 2, gets 2 next to it, so line 3. We've got the information that we need. We have the two pieces up here that satisfy the rule. So we need both of those. We got the square here, we got the circle here, so we're all good. We can just go ahead and put them together. So I'll put circle and square together. And here, I'm going to cite it 1 and 2, ampersand in. You may think like, well, how come we're doing it 1 and 2 when the circle's coming first? Why don't we do it, why don't we say 2, 1, ampersand in? And the truth is you can do it either way. It doesn't matter the order of the numbers that you put here in your justification. If you think it makes more sense to put 2, 1 instead of 1, 2, you can go ahead and do it. What matters is that the justification line is pointing to us, hey, this is where the information is that allows me to use this rule. I'm looking to use this rule. I need these pieces. Where do those pieces appear in the proof? Well, they appear in these line numbers. And then what's the rule I'm using on those line numbers? Well, I'm using ampersand in here. And then same thing as before. You could cite 1 and 2 if you feel more comfortable doing 2 and 1 because that's the order in which they appear here, because you have the left side here and then the right side there. You can do that too. It doesn't really matter. I usually just go in numerical order. Just makes more sense to me. But if it makes more logical sense to you to list them in the opposite order, that's fine too. Logic is just saying we have these sets of rules. You have to tell me how you are successfully doing these sets of rules by saying where's the information and what's the rule that you're using. And you have to go step by step by step by step. As we move on through this course with natural deduction, these problems will of course get more complicated, we'll use multiple rules and multiple or in the same proof. And so again, the idea is to be able to keep track, to cite what you're doing and say where your justification comes for doing what you do. So let's move on to the ampersand in examples. Now I'm just going to put our rule up here again for ampersand in. So we're going to have a square, we're going to have a circle, and then we can put them both together. And it doesn't matter which order we put them in. It just matters that we have the information up here, that we have a square by itself and we have a circle by itself. So the most basic version of this is just P and Q. I meant P, Q, therefore P and Q. So we'll just list our premises again. Our premise here, premise here, premise here, premise here. And then we'll mark those as assumptions for our justification. We'll associate the number 1 with P since it appears on line 1. We'll associate the number 2 with Q since it appears on line 2. And so now what we'll do is just use our rule. We have a square, we have a circle, so we can just write square and circle. What's in our square? We got a P. What's in our circle? We got a Q. Where are the P, or where does the P come from? It comes from line 1. Where does the Q come from? It comes from line 2. What is the rule that we're using? We're using ampersand in because we're putting them together. What we're doing is we're putting an ampersand in between the two things that we found previously in our proof. So with that, we look at what's next to line number 1. Well, it's just line 1. What's next to line 2? It's just line 2. And so that is that proof. And again, if we wanted to, we could flip these over. And the proof would look the exact same. Just with those two pieces getting flipped around. So it still abides by our rule up here, which is to say I have a square, I have a circle, and then I'm going to put them both together with an ampersand. It doesn't matter the arrangement that they go in, it just matters that they get put together. And keeping consistent as I did with the previous slides, let's just look at one that looks a lot more complicated than that one does. Not gonna get room if I do it bad. And actually, I have to drop this down just to be able to make it fit. Actually, I might be able to just shorten this up. Alright. So just imagine that this conclusion here is all together on the same line. It shouldn't be broken up like that, but it'll work out. This is just for showing you that the same thing applies as before. So we would list our premises. Just as one premise. Here's another premise. And 1 and 2, they would both be assumptions because they're both of our premises. And from these two premises, we can build our conclusion. We just take this as our square, this is our circle, and we can just put them together. Not P and Q and L. I'll put an extra set parentheses there. L arrow M and not N, like that. And then that's going to come from 1 and 2. What are we doing? We're putting an arrow in, or we're putting an ampersand in. Justification, or the premises for it, will come from there. So it's the same thing as we've got here on the left-hand side, here on the right-hand side. We have a square in the not P and Q. We have a circle in the L, arrow, M, and not N. And then we just put them both together because it says if I have this thing and I have this other thing, then I'll just put an ampersand in between them and match them up. It's like saying I have a 2 and I have a 3, so I can write 2 plus 3. It's the same thing. It's probably how most calculators work, using logical sequences like these here. So again, this looks confusing. I know it does. You're like, what in the world is going on? But the important thing to understand is that it follows the same principles as this one over here on the left-hand side. This one's as basic as it gets. There's only the one operator, and it's the main operator. But it's the same thing here. You're putting something together, and you're making the main operator the ampersand. You're taking two pieces, and you're just putting them together. So those are the ampersand in examples. Finally, let's just look at a couple of examples in which we have a combination of these rules operating at the same time. So this first one, let's say we have as a premise P and Q arrow R. And then we also have P, Q as premises, and we're looking to derive R. So we have three different premises. We have this one here, we have this one here, and we have this one here. So we're going to list them. It's the first step in every proof, is just list your premises in the first lines. And then this will just keep track of our line numbers. I usually just put some extra numbers down below. I don't know how many I'm going to need at the very beginning, but I can always erase or I can always add more. It's just an easy way of doing it. So we're going to mark each of these with an A because they are premises, they are assumptions that we are taking into consideration. So every premise is always marked with an A, like we see here in our justification line. Now, this becomes, oh, well, also before we get going, we want to assign these different numbers where the assumptions are introduced. So 1 for 1, 2 for 2, 3 for 3. Now here becomes the sort of fun thing about logic, because logic is just a critical thinking, sort of try to solve this puzzle. We have a puzzle. We are looking to get to R by itself. That's the conclusion. That's the goal. Our last line in the proof should be R all by itself. The first step you'll want to do is identify where that letter is in your proof. Well, the only place I have an R is in this first premise. Well, now that I've located where R is, I know where I'm going to be getting it from. What's the main operator operating in that line? Well, it's an arrow. So what's that telling me? That's telling me that I have a square arrow circle, and I'm looking to get the circle by itself. So we know what rule we should be using already, because our arrow out rule says I have a square arrow circle. If I get the square, I can derive the circle. So I know my last thing is going to be arrow out. That's how I'm going to get this R. So I have this piece already. I have a square arrow circle. I have this is a square. My R is my circle. So I've already got that piece. Now I'm looking for my square. Do I have P and Q together? Well, no, I don't. So I'm going to have to construct it. Can I construct P and Q from what I have in my assumptions? Well, of course I can, because I have the ampersand in rule that says if I have two things, I can just insert an ampersand to put them together. And look, I have the P and I have the Q. So I want to build the square that I have here in line 1 in my conditional statement, in my arrow statement. How do I build it? Well, I put these two pieces together, P and Q, using this rule here. Where are P and Q located? What line numbers? Well, P is on line 2. Where is Q? Q is on line 3. What's the rule I'm doing? Well, I'm introducing an ampersand, like that. And then we just need to do our premise lines over here on the left-hand side. So what's next to the 2 is a 2. What's next to the 3 is a 3. So I will just put 2 and 3 right here. So my 2 comes from here, my 3 comes from here. Now I've built my square. That was the other piece that I was needing to make this proof happen. Now that I have it, I can check mark it, say I've got it. And so since I have these two pieces, I've got an arrow, and I've got the left-hand side of the arrow, namely that right there. I can go ahead and derive the circle, which the circle is just R by itself. And so since I have the R by itself, that's what I'm looking to prove. Now let's just see where my justifications come from. So I'm looking for where my arrow is. Well, my arrow is here in line 1. My square is here in line 4. What's the rule that I'm using? I'm using arrow out. And then finally what we have to do is what's the number associated with line 1? It's just 1. What's the numbers next to line 4? Well, that is 2 and 3. And so that is the proof. Just as a general note, and most of these proofs that we do here, especially early in the natural deduction section, you will see all the premises here at the very end of the conclusion. It's very unlikely that I'll ever give you a premise that you don't need. All the premises will likely need to be used in one way or another. So you'll always see all the different premises at the very end of the proof. Once we get into provisional assumptions and stuff like that, when we do arrow in, tilde in, and tilde out, it'll be a little bit different. But for right now, just know that that is the uh, likely result that you will see in each of the proofs. But there's one. Let's do just another one real quick that looks very similar to that one. So instead, this time, let's do P arrow R, and we have P and Q, therefore R. So here, let's say we've got our premises, P arrow R. I don't really need these parentheses there. P and Q. We'll mark them with assumptions, just like we did before. So I've got two premises. They are both marked with assumptions. So I have line 1 here, line 2 here. So because those are wherever our assumptions appear at. Now, same sort of strategy as before. Let's look at what we're looking to prove, because what we're ultimately going to end up with is R. And where do we see R? Well, we see R here in our conditional. It's the only place it's not in our other premise. It's only in this premise. And what's our main operator? Our main operator in that line is the conditional. So I know I'm going to be doing the same thing as before. I'm going to be looking for all of these pieces. I'm going to look for the conditional, which I already have. It's given to me as a premise. And then I'm going to be looking to derive square somewhere. What's my square? My square is just P by itself. So I need to find a way to just get the P by itself somewhere in this proof. Well, can I make that happen? Well, sure I can. In line 3, I can separate this P from this ampersand by going from line 2, because I have an ampersand in line 2, and what am I doing? I'm getting rid of it, so I'm taking it out. So it would be 2 ampersand out. So I have, just for a visual here, I've got a square and a circle. What am I doing? I'm just separating out the square from the square and circle. That was our rule here, right? So what number is associated with line number 2? Well, it's just 2, so I'll put 2 here. And now, this happens to be the other square I'm looking for in my proof. That's what I'm looking for here. And so, since I have a conditional in this first line, square arrow circle, I have the left side, I have the square, I've got the antecedent, what we call it in logic. So, since I have those two pieces, I can derive the right side from it. So that would be 1 and 3. What's the rule I'm using? I'm using arrow out. And so what's the number associated with line 1? Well, line 1 is 1. What's the number associated with line 3? It's 2. And so I cite those here in my premises, justification area, and that is the whole proof for that one. So again, we have multiple rules that we just saw in previous slides that get used in conjunction to prove this. So from here, we'll do some more examples as to how to sort of use these 3 rules effectively to derive the conclusions from the sequences that we're given.